now that we have resistance, the concept of resistance, and I can look at, actually, let me put it like this. We have the resistance of a piece of material defined such that the resistance is equal to the resistivity rho times the length of the object. The longer the object, the higher the resistance. The higher the resistivity, the higher the resistance, divided by the cross-sectional area. Because the higher the cross-sectional area, the lower the resistance. If we're going to make this anthropomorphized model, the easier it is for the electrons to run around each other. Now, one advantage is that we have materials in which the resistance is far higher than the resistance in most metals. Now, it also behooves us to use those materials because from Ohm's law, the current going through a wire in an ohmic material, is equal to the change in potential over that material divided by the resistance R. So, current is what is most dangerous to us when interacting with electricity. So while there are cases where we want to have very, very low resistances, we must be very careful when we set those up. In most cases, especially most cases that we could do in a lab or sitting at our table looking at what the heck is going on in front of us, we will have the resistance concentrated in very specific resistors. And I will write the resistor in a circuit like so. Now, let us look at a circuit containing one resistor and one battery. In the analysis of circuits, well, this will drive a current, since this is defined as the positive side and the negative side. This will drive a current from positive to negative through the circuit. We have two rules that are going to help us in these analyses. Those two rules are the conservation of current, that if I reach some sort of branch point where two or more wires together, or for any element, a branch point, a resistor, anything, the current in has to equal the current out. Current cannot simply be, created or destroyed. Secondly, if I am going through a closed path, suppose I take this eraser, I move it from this tabletop to up here, down to the floor, pick it up, move it back and forth in the air, and then put it back down where it started from. One thing that you can say about that total trip is because it ended where it started, the change in potential energy had to be zero. Cases where I had to put work into it, I let go, work comes back out. So, this is for an element and then over a closed loop everything starts where it started from, over a closed loop, the change in the potential has to be 0. So if I'm looking at this single loop circuit, the change in the potential as I move from negative to positive over the battery is equal to the EMF of the battery. In the same way, as I move over that resistor, the change in potential over that resistor has to be equal to the EMF of the battery. Now, suppose I have more than one resistor. And actually, we're going to look at some of this a little bit later. R1 and R2. What I can say is, okay, I've got some change in potential over resistor 1. And I've got some change in potential over resistor 2. The change in potential over resistor 1 plus the change in potential over resistor 2 have to be equal to the change in the potential over the battery, because over one entire loop, this will go up by that EMF of the battery. As I go with the current over the resistor R1, the potential will drop. As I go over the other resistor in the direction of the current, the potential will drop. I end up back where I started from. That sum has to be 0. Over a single loop, we've done one thing that's going to help us in a couple of seconds, but we've set something up that will be very helpful to us in more complex circuits. Coming right up.